pleasure to have here Lars Arvestad. He completed his PhD in computer science at KTH Royal Institute of Technology in 2000, after which he briefly worked at a pharmaceutical company, and he went to hold on several research and teaching positions at Karolinska Institute and KTH, and eventually he became a lecturer at KTH. Since 2010, he is actually an associate professor of computer science at Stockholm University. So his research interests lie mainly in evolution and sequence analysis, particularly regarding questions along the orthogonal axis of improving models and improving methods scalability. So thank you again for accepting the invitation, and the floor is yours.
Thank you. I'm very happy to be invited here, actually. And what I want to talk about is scalable distance-based phylogeny inference. And one might think that, wow, not distance-based phylogeny inference again. We all know about neighbor joining, and it's not a very good method, really. If you want a good tree, you should use maximum likelihood or some kind of Markov chain Bayesian method of some sort, and there are plenty of tools for doing that. But I have the first excuse in that I stumbled on what I want to present on by chance. So that's a good reason, right? And the other is that, well, distance-based methods are still used as subroutines. So they are an essential part, especially now when the problem sizes are growing and people are interested in larger and larger trees. And I think in this company, everyone is familiar with what the computational problem is, but let's just start there. And yeah, I'm looking at the input as sequences, biological sequences, but any kind of entities that you can compute distances between. And what we want to produce is an unrooted binary tree. And this is not just any arbitrary tree. It should explain the data nicely, in some loose interpretation of what explain means. And basically, in the distance-based context, of course, you want that the distances that you can compute over the pairs of sequences should be reflected and be close to the distances in the end product in the tree, so to speak. But the distances or branch lengths in the tree are not important, and I'm not considering that as part of the output, at least in this presentation. So I'm guessing that everyone participating is familiar with neighbor joining, but let's just reiterate that as well. So it's a greedy method where you pair up taxa or sequences to create a tree. And this is illustration I stole from Wikipedia. And yeah, it depicts intuitively how you go around in this algorithm. And so the central part is really how you pick these cherries for the tree that you're creating, pairing up the taxa. And that is, of course, done with the neighbor joining selection method function that can be written like this above. And the main issue with neighbor joining is that it's slow. Since you have to update your distance matrix fully in each iteration, you get the cubic time complexity. And that's definitely prohibitive and has been prohibitive for a long time. But when the data sets grow, it just becomes infeasible to work with. Still, neighbor joining gets good results, and that is in part, I guess, because of the fact that it's behaving nicely, and that's perhaps best captured by this convergence radius that Atchison found, which is that if the errors are small, and at most half of the distance of the shortest branch in the tree, then and neighbor joining is guaranteed to return the true tree, which is of course a very nice feature and a really cool result altogether. So this problem of neighbor joining being slow is really the main problem. Now the good news then is that there are speedups available. So my colleague Jens Lagergren, he came up with a method he called fast neighbor joining, and this method is inspired by the proof of the Atterson's convergence radius. So he changed the objective function to be somewhat different, and it's not neighbor joining as such, but it has the same basic properties, at least when the errors are small. So then you're guaranteed the same result. But when you have larger errors, neighbor joining keeps on shining, but if fast neighbor joining is doing a little bit worse. And Simons and Milan and Pedersen, they worked on a tool they called RapidNJ, in which they start off with neighbor joining and tries to find out shortcuts in the computation that works most of the time. And you all often get runtime which scales quadratically, if you may accept that phrase. And but you are essentially computing the true neighbor joining algorithms still. And therefore you have very nice behavior and nice accuracy in the estimation. So we have changing the heuristic somewhat, and in two different ways as two possible ways to go. But you can also work on the engineering side of the problem if you want to make neighbor joining work feasibly. And last year we had Wang et al. From the, yes, you can call the IQ crowd that presented a tool called Descent Tree, which I think was inspired by their efforts in making COVID phylogenies. And they simply started their work, as I understand it, with RapidNJ algorithms, but worked more on the engineering side and added parallelization, for example, making a very quick and fast tool. However, regardless of which avenue forward you start, if you change your heuristic or if you improve your engineering, you will still have some limitations here. And this limitation is due to the fact that you need distances as input, or rather a distance matrix. So you have quadratic number of distances to be computed, and each of these distances needs at least the time scaling as the length of the sequences. So essentially this is cubic time. And if you have a pipeline of two jobs to be done to be able to produce a tree, it's of course the time complexity of one of those that will dominate, and in this case it's the distance estimation. So using any kind of distance-based method is essentially cubic time if you have to compute all the distances. So how do you avoid that? I mean, do you really need to compute all the distances to be able to estimate a tree? I mean, intuitively, there should perhaps be some possibility there. Well, as I mentioned, I kind of stumbled on a trick to avoid doing that, and I want to tell you a little bit how that looks right here. So this is a divide and conquer approach. So of course we need the base case, and this base case size, well, that can be, I don't know, whatever is suitable for your computer. So let's say, but you think of it as 100 sequences, and that's a small problem size, so you can easily compute that distance matrix and return a neighbor joining tree. However, if you have more sequences like that, I think one should randomly pick 3 of those taxa from the input and compute a tree and sort of a center vertex that's going to define sub-problems for you. Because these sub-problems are going to be used recursively. And what we do with all the others, except for these 3 input vertices and the center vertex, is to just go through them and figure out in which sub-problem the sequence kind of belongs. And we do that perhaps by using the neighbor joining selection function, or you can use quartet experiments or something like that, but it doesn't really matter. There are natural ways of doing this. And then we prepare these 3 sub-problems, which are disjoint almost, except for the fact that they share this center vertex. And then these 3 sub-problems are, of course, smaller, and we can well, it doesn't matter. We have reduced the problem size, and we can hand off these sub-problems recursively. But when we get them back, it becomes easy to construct a common tree for all the taxa again, because the sub-problems were independent. They only shared one taxa, and that was this artificial center vertex. And what one can do then is to glue them together, these 3 trees that we computed recursively based on this center vertex. So the way I like to think of these things is that I work with a base case or with a partitioning, or I make use of 3 friends to take care of the smaller sub-problems for me. And then my 3 friends can return these 3 trees, and thanks to the fact that we have one common vertex in between them 2, and that vertex is artificial, so it will be in the internal of the tree. It's super easy to put them together. And yeah, this is surprisingly easy to program. It's very straightforward, and I did that. And the little detail here about the speed, and of course, is that how many distances are we actually computing, and how many are my friends taking care of? Well, I need a small fixed number of distances to be able to find this first triplet tree, and then delineating the 3 sub-problems. Well, I go through and compute a linear number of distances, 1 vertex to the 3 other vertices in the starting tree, so to speak, and make some additional work. So altogether, just for this recursive step, we use O of n distances, which is cool. So it's easy to implement, and if one can get these sub-problems to be of basically the same size, so you will get essentially n log n time here, which is very nice. But then if it's unevenly balanced, which does not happen so often in practice, it seems, well, then you will get quadratic scaling, which is still pretty good, actually. So that's nice. And the effect of that is the fact that we're avoiding many of these pairwise distances in each step. So on each recursive level, we do a linear number of distances. Well, you avoid, in practice, a large fraction of the distance matrix. So here I've tested this with base case sizes of 3 different sizes, from 50 to 200 sequences, and increased the number of leaves in the tree, so the taxa in the input. And as you can see, the fraction of a distance matrix that is actually needed by this recursive method, it diminishes super fast. And this is the main feature of this algorithm. It's truly scalable, and I will come back to that a little bit later. And another nice thing is that Addison's convergence radius is actually respected as well. So as long as the distances are good, well, then we are guaranteed to return the true tree. And to experiment with this, I put this together in a Python program. And in my first experiments, I've worked with simulated distances. I wanted to understand how good this algorithm was, both in terms of speed and in terms of accuracy. So here's the protocol. We see I decided on a tree. So this is not very good testing, really. This was my first testing, so I'm sharing my first experience with you. And all the branch lengths are 0.1, so it's super easy. And I'm just making that tree up, nothing random at all. But the errors that I add to this fixed tree, they are random. And within some kind of error interval, taken uniformly at random. So then I'm running the DNC tree, which I call both the algorithm and the software, to get the tree, and then I'm using relative Robinson folds to compare the true tree with the estimated tree. And I repeat that 100 times. And here's the result I get on this simple test. You have the dependency on the error down on the x-axis, and then on the y-axis, the relative Robinson folds. And then I've used 4 different base case sizes here. So with k equals 10, I start using neighbor joining when I have at most 10 sequences in the input. And in the red bar, it represents having up to 40 sequences on the input. And the purple, which you barely see actually, right? It's down here primarily. That's the true neighbor joining. But you can see that if the errors are small, well, then I'm getting the same results as neighbor joining. But as soon as we start getting larger and larger errors, DNC tree is increasing in inaccuracy. So not very good, actually. Neighbor joining is maintaining its accuracy very nicely down here. But it's fast. So it's super fast. And that's really what I was aiming for, in a sense. So I'm not so happy about it being fast. I'm wrong, I guess, but I'm super proud of this method being super fast and really scalable. And okay, yeah, so why I can start worrying about this? Why, or at least I did. Why is this so bad? Then why is the behavior of the DNC tree so bad? I mean, 0.8 as we're reaching up here, that is really bad accuracy when you're comparing with Robinson folds. And yeah, I mean, it has to do with the fact that it's a very greedy algorithm, of course, but so is neighbor joining. But in every step here, in using the DNC tree, we're only using 4 sequences. So we have a base case where not a base case, a first step in which we pick out 3 sequences. And then using these 3 sequences, we're trying to take every other sequence and figure out which subproblem it belongs in. So in every step of this algorithm, we're looking at most 4 sequences at a time, and when putting them together. And okay, that's good for speed, but it's probably bad for accuracy. And compare that with neighbor joining, when in every step, you're using the information from all the sequences when choosing which pair of sequences to join. And I was thinking, there should be a middle ground. There should be a way of using more than 4 sequences here, but still not have as many sequences as neighbor joining. And that led me to look at an alternative of divide and conquer of the DNC tree algorithm that I made up, and I asked bachelor student Amy Jalsenius to work on that, and she did a terrific job at fixing things nicely. And this reformulation of DNC tree, which we call DNC tree K, due to a new parameter here, is that instead of starting with 3 sequences to define our subproblems, we're starting with K sequences. And in this example up here, we're having 7 sequences. So K equals 7. And we pick those K sequences to form a core set of taxa. And we can, on that small core set, compute both the distance matrix and a neighbor joining tree. For example, one can consider other methods too. One should probably try using a maximum likelihood tree as well. But the next step is then to, in this tree, compute the center. And the center is a vertex in which the maximal distance to any leaf is minimized. So the intuition is that it's really the middle of the tree. And in that, technically that's either 1 or 2 vertices, but we pick the first one we can get our hands on. And this center sequence is, again, defining the subproblems for us. So we compute the center tree and see what subtrees it partitions and what how the core taxa, the ones we picked out as a start, how they are partitioned using this center sequence. And these will then form the first 3 subsets that will induce our subproblems. And what we do next is similar to the first algorithm, go through and decide in which subproblem each of the other sequences belong. And the way we solve that is by looking at the neighbor joining selection function and to see which mate in the core tree or that or in the core set that the selection function thinks is best. So we've created these 3 subproblems, and what we do is to join the center vertex into each of these subproblems, compute the necessary artificial distances that are needed for this artificial sequence to all the other sequences, and then recursively compute trees again using the same algorithm. Eventually, of course, a base case will be returned and we can build up things. And we build it up by connecting these 3 subtrees that have been computed on the shared vertex C, and then we're done. So how does this algorithm work in practice? Well, it's still easy to implement, surprisingly easily, and suddenly the accuracy goes up a lot. So we did the same kind of experiment with simulated distances at first. So it's the same protocol with one chosen artificial tree and then a simulated noise. And please note that now in the second version, the left figure is the same as before, bad behavior, but the y-axis now is drastically lower, right? So the performance or the accuracy is almost in line with neighbor joining if you have large enough base case size. And in fact, there are up here that you can notice that the difference in accuracy is not even necessarily statistically significant one, I would say, just claiming that to see what happens here. But I, of course, felt that this needs to be investigated further. So I started creating simulated alignments using the algorithm AliSim from IQ3. And in this tool, we are randomly picking a random tree on a certain for a certain number of leaves, and then simulating sequences in this tree. It's a standard random model of trees and sequences, one can argue. In this particular case, I used a multiple sequence alignment of 500 columns, and then increasingly large trees, as you see. And for each combination of parameters, I used 100 alignments, so 100 replicates, and computed the average error using relative Robinson folds again. And in this case, as you can see, it maxes out a little bit nicer. So the simulated distances with the simulated errors was a bit harsh, one can argue, than what you get with real simulated alignments. I'm not sure that's a good term, but I hope you can agree with me that this kind of simulated data is better than the simulated distances. And one can also, so this is with the worse algorithm, the only having a starting tree of 3 sequences. And then if we do the same with DNC3K, which is the more evolved one, where we have a base case size and a core size of equaling K, that is, the base case size and the size of the core tree is the same. And then I found that the behavior was so much better. It's amazing. The y-axis here is completely misleading. I was kind of having a hard time understanding this when I saw it, but the error in estimated error is very small compared to what I saw on the first grid algorithm. It really helps bring in more sequences in determining the subproblems. So further investigation was needed, and I started comparing with other methods. So RapidNJ and FastTree, which is a tool that many people like to use for large instances with many sequences, and BioNJ for a high quality true neighbor joining method. So FastTree is well known, I think, for its sort of profile distance, which then has been amended with both a tree editing step and a maximum likelihood evaluation step to improve accuracy. And to make this comparison meaningful, I decided to not use the maximum likelihood step. And that's a post-processing step that you can apply to any distance-based method, I'm arguing. And I tried with and without the tree editing step. So what you see up on the top here, that's the performance of FastTree without the tree editing step, where you try to fix things step by step to improve. And the accuracy of that is comparable to the first DNC3 algorithm that I came up with. And of course, it obscures the performance of the other methods. So I removed that method in the second figure that I have here. And it's still no maximum likelihood evaluation in FastTree. But then we can see quite clearly that both the neighbor joining methods are actually doing much poorer than both the FastTree with tree editing and DNC3, at least for well, regardless of the base case size for DNC3. And for both fast tree and DNC tree, you basically have no accuracy problem at all when the number of leaves are increasing. And fast tree is doing better, of course, but I feel that isn't that a little bit of an unfair comparison? After all, this is with tree editing. And if you added tree editing to DNC tree, well, then you would get that come down as well. So I'm super happy about that. I want to point out that it's a fair comparison in a sense. I haven't spoken much about how distances are computed, but my starting point has been that this should work with protein sequences, and the models for protein sequences are very simple that are implemented in RapidNJ for scalability and speed issues. But in my testings, I've used standard model like Whelan and Goldman or KTT, or those standard models to estimate protein distances. High quality distance models, one can point out. And I've used the same distances for all the tools. So it's a pure tree comparison that is being done there, except for a fast tree, which is working with profiles. So trying to summarize this, I presented two scalable neighbor joining methods that use divide and conquer. And one is super highly scalable, but with low quality. And the other one is scalable, but of high quality. And what's good to know is that no distance matrix is actually needed. So in principle, one can start experimenting with distances without multiple sequence alignment. And it's something that I've tried to explore but run into practical problems with. And I want to point out that this is simple to implement as well. And I've done it. And I have a tool available that you can try today. It's easy to install and easy to work with. Thank you.